Today we're going to learn about heat engines, and we're going to do it by experimenting with different heat sources on a Stirling engine. In order to get more power out, we need to make the hot reservoir hotter and the cold reservoir as cold as we can get it. We'll run the engine in a range of circumstances, culminating in trying to answer the question, can we run a heat engine on liquid nitrogen?
Hello, welcome back. Today we're going to take a look at the Stirling engine. This is a miniature Stirling engine and it operates on the principle of the difference in temperature between a hot reservoir and a cold reservoir. Here we just have a coffee mug underneath. This is the engine itself. Let me go get some hot water and just put hot water from the tap onto the hot reservoir on the bottom. We'll begin to see the engine turn and we'll talk about how it works. What we'll do is we'll increase the temperature gradient between hot and cold side all the way up to liquid nitrogen to see how fast we can get this thing to go. And I haven't actually done it before, so I'm curious to find out for myself. All right, so I'm back with some hot water. This is not boiling, it's just hot water from the tap. So I'm gonna pour this water into the mug about a centimeter away from the top or so, and we'll put the Stirling engine back on the top here. So what's happening now is there is a plate on the bottom of this engine, and then there's a material that kind of seals this inner cavity off. It's kind of a gasket on the inside, or a bellows. And then there's a top plate here. And what you want to do is introduce a temperature difference between these two plates. Now, nothing much is happening because it takes a second for this thing to warm up enough to do anything. That actually there's internal friction in the turning mechanism here. So what we have to do is give it a little bit. If we made a very hot boiling pot of water, then it might start on its own. But since it's just kind of like a little bit above room temperature, we need to overcome the friction ourselves. So what we'll do is we'll just kind of like get it just going, and we'll start to convince ourselves, hopefully we'll convince ourselves that the engine will run under its own power. So we'll just give it a little bit of a helping hand. So what we have is a hot plate here, a hot reservoir, so to speak, and a cold plate or a cold reservoir on the top. And as the heat flows into the bottom plate, what it does is it heats the gas up, the air that's inside of this sealed container between the bellows that's going up and down, that's kind of like sort of sealing the two halves off. And what's happening is we're heating the air underneath this moving member. As we heat the air, it wants to expand. So it pushes the bellows up, and then it pushes the crankshaft, the push rod here. There's two push rods, one on either side, and it's basically pushing it up and turning the wheel. But as the flexible member on the inside gets to the cold side, then it cools off. And that cooling off effect gets transferred again back to the air inside of there, and it tends to cool the air off. So the air inside tends to contract, and then the thing moves down again. As soon as the internal member gets to the bottom of the hot area inside, it gets hot again, and then it causes the air to expand, and the process repeats over and over again. So there's expansion and contraction of the gas inside of there brought about because of the hot side of the plate and the cold side of the plate. So it's not moving very fast, right? We can actually calculate the RPM if we time it for a minute, and then we can see like how many RPM this thing is running. Now, in order to make it go faster, there's a couple of different things we can do. We can put hotter and hotter water in there, and we are going to do that. But in addition to putting hotter and hotter water in, can you think of another way to make it go faster and get more work out of it? Well, we can make the cold side colder because it's really working because of the hot side working with the cold side. When the air gets hot, it pushes that bellows up, and then when it gets to the cold side, the colder it is, it causes the internal air to get colder and contract again. So if we could make the hot side hotter, it should go faster, and if we can make the cold side colder, it should go faster. So let me leave this water in there. Let me go get some ice cubes without changing anything, and we'll see if we can get this thing to go faster just by adding some ice to the top. All right, so now I'm back. Let's just take a couple of ice cubes and see if we can put them on. Now, it's a little tricky to get them to stay on there, but I haven't changed anything. I haven't increased the temperature of the water inside. I haven't really done anything at all. I just walked out of the room and got some ice. Of course, it's a little difficult keeping the ice on there. When we do our dry ice in a minute, I'm going to fix that little problem. But let me see if I can get this thing. You can already tell that it's starting to speed up. So I'm going to put some ice on this side. And I think you can tell already just from the sound of it. I think you can see right away that just by cooling the top plate, we're able to get this thing to turn faster, right? And the reason is because when the expansion and contraction process is happening faster, when the internal member gets to the top, it's hitting a colder reservoir, which is causing the gas to contract faster and then start the process over again. So what should we do next to get this thing to go faster? Let's, instead of water ice, which is 0 degrees Celsius, we're going to leave the same water in the bottom and we're going to put dry ice on the top, which is much colder. All right, now when we put dry ice on the top of this thing, it's at a temperature of -78 Celsius, so much colder than water, which is at 0 Celsius. It's not going to stay on this thing very easily. So what I have here is actually something I bought, which is called copper tape. It's essentially a metallic tape with a sticky backing, and that's going to help conduct the heat down into the top plate. And that's going to help keep the dry ice and later the liquid nitrogen on the top plate and actually help also conduct the heat on that top plate. So what we're going to do here is just peel this thing off. And what we will do is try, I don't want to cover up the bellows down below. I don't want you to not be able to see what's going on. So I'm going to try to connect it all the way around. Okay, here's our last piece. We're going to connect it right in there. Try to seal it, because later when I put liquid nitrogen on here, it's going to help to contain it and also to conduct the heat there as well. So here we have a little boundary of copper tape there. Let me get the hot water, get it going, and then we'll add our dry ice to the top. All right, so here we go. Let me move our Stirling engine out of the way. We'll put our coffee cup back. This is just, again, hot water out of the tap. I don't know the exact temperature, but it's not boiling. It's pretty hot. It's probably about as hot as you would drink tea or coffee or something like this. And then we'll put our Stirling engine back on, and it'll take a second for it to warm up. And while it starts to warm up, let me break up my dry ice. All right, let's see if we can get our engine going here. Let's see if it's hot enough yet. So we'll kind of start the process. And it's starting to kind of wake up. So let's just give it a little more help here. Make sure it's in the steady state. Make sure it's really going. And we just added water ice, which is down to 0 Celsius. So we put the top plate pretty close to 0 Celsius. We saw that it was moving pretty rapidly. Now we want to do exactly the same thing with dry ice, which is 78 degrees below 0. So we're making that temperature gradient much, much wider. Now it's going to make some noise when I put the dry ice on top. Usually it likes to slide around and make noise. It's just the way it goes. Dry ice is frozen carbon dioxide. So what's going on is as it sublimates, it turns directly into gas, and then it starts to slide around on the surface wherever it is. Let me put some on this side. All right, we can see it moving much, much faster now. I think I missed one little spot. Need some ice right there. Let's let it finish doing its little jiggle. And so you can see it moving much, much, much more rapidly when we have a hot reservoir slightly below boiling and a cold reservoir 78 degrees below 0. So now how do we kick it up a notch? What I'd like to do next is I'd like to go get some boiling water, so we know that the bottom reservoir would be at 100 Celsius, and then we'll do ice cubes, and then we'll do dry ice, just widening that temperature gradient to see if this engine, how fast we can get this engine moving. So let me go get some boiling water. We can see this thing is really cooking now and moving significantly faster than it was before. All right, here I'm back with boiling water. I want to do it very, very quickly so I can keep the temp up in this guy. So here I have boiling water straight out of the kettle, actually the microwave. And what we'll do is we'll start it. We'll just see what hot water does. So we have a very hot reservoir. And then after that, we will put ice on, and then we put dry ice on. So let's just let it sit there. Sometimes it can start on its own. So here we have the boiling water. Let's give it a little bit of a friendly start. Notice I didn't have to push very hard at all, and the process begins, right? And already, without doing anything to the cold reservoir on the top, we have a very established cycle, very, very nice, almost as good as it was a minute ago when we had the dry ice. All right, here we go. Let's see if I can put these on here without messing too much up. There's one. Another one. Oh, it's getting in the way. I don't want it to be in the way there. Drop a small one over here. All right, we'll let it cool down a little bit. I can already tell, because I can hear it, that it seems to be moving a little bit faster. and then we'll immediately go into the dry ice. Yeah, you can tell this is definitely faster than it was just a second ago. So let's reset new boiling water and then dry ice and see if we can hear it and see it get a little faster. All right, so here we have the boiling water again. We've reset, so let's go ahead and let that. So we'll do our dry ice. I'll just drop them on there. And it might start on its own. You never know. Let's see. It just depends because it has to overcome the friction, the initial friction, just like pushing something across the carpet. It has to overcome the initial friction, and then the cycle can kind of take over and overcome that static frictional force. Okay, so we have 100 degrees Celsius on the bottom and negative 78 degrees Celsius on the top. So here we go. Let's give it a little bit of a start. Notice we didn't have to push it hardly at all, and it's already up to speed much, much, much faster than the last time. So we'll just kind of let it cool down because I've noticed that it takes a minute or so for the top plate to be cold soaked and for the bottom plate to be hot soaked, for lack of a better word. So you can see right away, I mean, just by my ear, I can see that this thing is operating much, much, much faster. The heat energy from the hot side is going in, expanding the gas. It hits that super cold plate and immediately starts the gas contracting and then over and over and over again. You can think of this as an external heat engine where the heat source is external and the cold plate is external to the actual cylinder. In a car, the explosion is happening inside. That's why we call it internal combustion engine. This is an external heat engine, also called a Stirling engine. Again, you get more energy, more heat, more work, the wider the temperature gap is. Let's go ahead and reset with boiling water, and then let's put liquid nitrogen on the top and see how fast we can get this thing to go. Liquid nitrogen is about negative 195 degrees Celsius. So whereas dry ice was only 78 below zero, liquid nitrogen is much colder, negative 195 below zero. So let's see if we can get it started. And we can see that it's already operating. And this is why I put my copper tape there to kind of help contain the liquid nitrogen. So it's going pretty good. Let's see what happens when we actually add liquid nitrogen to this system. All right, let me go on this side, I think. Right? Negative 195. And it boils away right away, but you can still get that plate very, very cold. So you can see this thing is really cooking now. Now what happened was that when I pour it on there, it gets so cold that it sort of seizes up. But then it kind of overcomes that, and you can just see, now as you can see, it's starting to seize up. So let's see what happens. This is kind of neat. I've never really done this before. So let's just let it kind of thaw out a little bit. Something in there is frozen up. You can start to see it cooking along really good here. Let me add a little more. It eventually will seize up because eventually something's going to freeze in there, right? It's not designed to do this. But you can see that it's working, quite well. Now, just for giggles, just because I like doing things, let's grab some dry ice, which is not quite as cold, but we can make a nice cloud. So let's drop it in there, something like that. And we'll pour some liquid nitrogen on top. And we can get a little effect there. So you can see this thing is really cooking now. Much, much, much faster than before. So 100 degrees on the bottom, negative 195 degrees on the top. And you can see it's really cooking now.
Here we can see a nice comparison in the two most extreme situations. On the left, the engine is powered only by a warm cup of water underneath and ambient room temperature on top. On the right, we have boiling water at 100 Celsius on the bottom and liquid nitrogen at negative 195 Celsius on the top. To me, it's absolutely amazing how much power we can get out of this engine by making the temperature gradient as wide as we can get it.
Hello, welcome back. So as we've said many times, the efficiency and sort of the work that you can get out of a heat engine is related to the difference in the temperatures between the hot side and the cold side. So it stands to reason then, right now we have this engine sitting here with no heat source underneath, it's just at room temperature. So in theory, if we just cool the top side without even heating the bottom, then we should get the engine to run because then the cold plate will be cold, the quote-unquote hot plate would just be at room temperature. So we're going to try it. We're going to put liquid nitrogen on the top without any heat source on the bottom, and let's see what happens. Now I have to be careful not to do it too fast, otherwise I'll basically freeze up the engine. So I don't want to do that. So I'm just going to put a little bit, let it slowly, I guess I'm kind of like walking around a little bit and let it kind of slowly get this thing cold. And then we'll just try it. We'll just try to get it to run and see what happens without any hot source down there at all. So we'll go this direction. So not quite enough yet. Let's add a little bit more. We're going to do it slow. I've done this enough to know that if I cool it too rapidly and just literally dump the liquid nitrogen on there, then it's basically going to, in that case, essentially seize up. So let's put a little bit more. All right, here we go. And there we go. Now we can see it's now finally cold enough. Without any heat source on the bottom, we're able to get this thing to run, because it's not necessarily the absolute temperature that matters. It's the difference in the temperatures between the hot and the cold side. So you can see not only is this thing going, it's actually going, at a pretty good clip. So I'm going to add a little bit more. Just to, I'll just kind of like slosh the bubbles around to get this thing moving nice and cool. I think it's running pretty good. Without any heat source on the bottom at all, it's running, right? Because the temperature difference is so great between room temperature and liquid nitrogen temperature. Heat engines, specifically Stirling engines, they work because of a temperature differential across the plates. Notice it's starting to seize up again, right? Because eventually it looks like it stopped there. I think I see what's going on. You get some ice crystals forming on one of the crankshafts. It just doesn't go in and out there. So I guess we'll just wrap up. So now we want to roll up our sleeves and dive a little deeper to understanding what we just saw there. You may have heard of something called the laws of thermodynamics, right? Now, when you dive into studying thermodynamics, you learn about engines in great detail, and you learn that the best engine you can possibly build as part of the laws of our universe, the laws of thermodynamics, is called the Carnot engine or the Carnot cycle. Every engine that we really have, whether it's an internal combustion engine or a Stirling engine like this one, operates on a cycle, some kind of cyclic process, and we're extracting work out of that device coming from somewhere else, usually a temperature gradient. And the best you can do is what we call a Carnot cycle. Now, I kept saying that it's related to the temperature gradient. Let me show you. I'm not going to prove it to you or anything, but we're going to write down what the efficiency of the Carnot cycle is, right? And the efficiency of a Carnot cycle, I'm going to draw a picture and show you what it is in a second, is the following. This is the temperature of the hot side of the engine minus the temperature of the cold side of the engine, all divided by the temperature of the hot side of the engine. Now you have to be careful because these temperatures are all in Kelvin. So they're not in Celsius. Kelvin is the absolute temperature scale. 0 Kelvin is absolute zero. You can never get to absolute zero, but it's the theoretical lowest you could go, and it goes up from there. So if you're ever calculating efficiency, do not put Celsius in here, put Kelvin in there. So what this means is that essentially the wider the temperature gradient you have across whatever engine you can build, the higher efficiency you're going to have. You take that temperature difference, divide it by the hot side temperature, and you will arrive at a number which will be a decimal. Now, in this situation, we're saying that the number 1 is like 100% and 0 is 0%. So you'll get some decimal between 0 and 1. If you could build an engine where the hot reservoir, the hot side, could be infinity degrees, so put an infinity Kelvin here, and the cold side we're at absolute 0, so 0 Kelvin there, and then you divide by the hot side, which is infinity, then you would get infinity divided by infinity, or if you don't like infinity, just think of a million. So if you had 1,000,000 degrees minus 0, and then you divide by 1,000,000 degrees, okay, so then the answer is going to be 1. So the best you could possibly do is to have a really, really, really hot reservoir and a really, really, really cold reservoir. And there are other limitations of the physicalness of your engine that you build, because no real engine can ever be a Carnot engine. But I just put this on the board because it's easy to look at and know what we were looking at with our physical engine, making the temperature difference wider across the hot and the cold plate seemed to get more useful work out of the device. All right, now we want to draw the cycle of this engine, but before I can draw, well, not of this engine, of the idealized engine, to learn what was going on here. But before we do that, we need to talk about work. Now in physics, you learn that work is force times distance. It's something we all learn when we take very basic physics. But I need you to connect that concept with the concept of work in terms of pressure times volume. Pressure times volume is not something you talk about much until you study engines, but it's the same as force times distance. The same unit of work comes out. I want to show you that real quick because I'm going to draw you a picture of an engine cycle, and I need you to understand this concept. So you might have remember from, high school physics or something, that work is equal to force times distance. Now I know that it's really F dot D because F and D need to be in the same direction, but I'm just assuming the force and the distance that the object moves are in the same direction, so it's just force times distance, right? Now what are the units here? The units of force would be in newtons. In physics, we use newtons. And the unit of distance will be in meters, right? So what you would have is Newton multiplied by meter, and that's the unit of work. But the unit of work, we say in physics, is the joule. So I want you to just kind of refresh your memory from basic physics that anytime you have a force pushing on something and it moves some distance in the same direction of the force, then the units of newtons multiplied by the units of meters gives us a new unit which we call joules, and that's the work done on the object. So force times distance, newtons times meters. Now in this cylinder here, we're going to talk about it in great detail. We don't have a single force and a single distance. We have the pressure of this gas in the reservoir, and we have a volume. As the cylinder moves up, it increases the volume of this gas down here, and as it goes down, the volume of the gas is decreased. So it's not just a distance that's changing, it's the volume of the gas we care about, and the pressure is the aggregate of the internal forces of the molecules colliding in there. So if you remember, what is pressure? The unit of pressure is just force, some force divided by some area. Right? We have many units of pressure, but it's always a force, either pounds per square inch or newtons per square meter or so on. In physics, we use newtons per square meter. This is the unit of pressure. And I'm telling you that if you take that unit of pressure and you multiply like a pressure of a gas in a cylinder, and if that cylinder increases the volume of the gas, then this means change in volume, then the pressure of that gas multiplied by how big the cylinder got, or how much bigger it got, the volume of the gas, what unit would we get? We just said pressure had a unit of Newton per meter squared, and we just said that volume of anything, some volume change of the gas as it gets larger, would be meters cubed. That's what the unit of volume is. But notice that you have meters squared on the top and meters cubed on the bottom, so we'll cancel all but one of those, and what we will actually get on the right-hand side is a Newton here times the single meter that's left over. But that's exactly what we just had here, which was a joule. So I need you to connect the idea that in high school basic physics, you learned that if you take a box and you push on it with so many newtons of force, then you've done work and the box moves, then you multiply those numbers and you get some work done on the box, right? And in the case of a cylinder, it's not a single force and it's not a single distance. It's the pressure of the gas, which is the force per square meter, so it's got a force rolled into that. And the cylinder doesn't just move, it does move some distance, but it's the whole volume of the cylinder that we care about. And when you take the pressure times an increase in the volume of the cylinder, you get exactly the same unit of work that we got over here, which is a joule. So in your mind, I need you to connect force times distance to give you work is the same as pressure times the change in volume also gives you work. Because pressure times change in volume, there's a force unit wrapped up in the pressure, and there's a distance unit wrapped up in the volume change. And so they give you the same thing. So when we talk about engines, we talk about pressure and volume all the time. So now what we need to do is I want to draw a picture of what this cycle looks like. Now, keep in mind, real engines are not idealized like this. I'm going to draw it on the board, but it won't be like a real engine, but it'll be close enough for us to understand kind of what this thing is doing. All right, so don't send me a message and say, oh, this isn't real because it's not real. Well, I know this. This is idealized, right? You study idealized systems in physics. Real engines are not ideal things. All right, so what we can do is we want to take a look at this cylinder. Let me draw a big thing here. And what we want to do is we want to plot some important things. I just told you the volume of this gas is important. The volume of the gas trapped in that little cylinder down there. And the pressure is also very important. Those two things, when you take the pressure times the change in the volume, they give you the work done on the gas or by the gas, right? So when I'm talking about the volume, I'm talking about, you see there's this cylinder thing, this little gasket thing that's in there. I'm talking about, we have the hot side on the bottom and we have the cold side on the top. I'm talking about the volume of that underneath the gasket. See, it's getting big there and then it goes down to zero, big, small, big, small. That volume down underneath is what I'm talking about when I plot on the board right here. All right, so what we're gonna do is we have to pick some starting point. So let's say we're gonna call this point A. And what we're saying at point A is that this engine starts out at some, it starts out at some pressure and some volume, a relatively low volume, but a high pressure, right? So that would be like when the gasket or cylinder, whatever you want to call it, is down touching the hot plate. The volume is very low. It's never really zero. You could call it something like this. And the pressure is, we're going to start it in the high state because it has to start somewhere. It's going to be a cycle. We're going to say it's in a high state because the hot plate down here is agitating the atoms inside and making a high pressure right there. What is going to happen as heat flows into the gas under this gasket? Well, it's going to put energy into it, and the atoms of the gas are going to start colliding, and it's going to try to push this piston up, right? And so what's going to happen is the volume of this thing is going to increase. But at the same time the volume increases, the pressure is going to go down, because when we increase the volume of something, if you hold everything else constant, then the pressure should be reduced. So we start at a high pressure and a low volume, but then what we do is as we add heat from the hot reservoir, it does something like this, okay? This curve is very, very important. So let me put the point B right here. What we're doing is we're adding heat to the gas, and I'm going to write down that by right along this curve here. I'm going to put a little arrow here, and I'm going to say QH. From the hot plate, Q is the symbol for heat. We add heat to the gas. Heat makes the cylinder get big. Now, it's a little weird because I'm saying the cylinder is getting a larger and larger volume, which means basically what's going to happen is this thing is going to get higher and higher towards the cold plate. It's getting bigger, and as the volume of the cylinder gets larger, the pressure of the gas goes down. Anytime you increase the volume of something, and you hold everything else the constant, then the pressure should go down. Now, importantly, I need to point out to you that this is an idealized process. We're just pretending that this process happens at a constant temperature. And I'm going to say that the hot plate is at 100 degrees Celsius. And it stays, during this whole process, the gas stays at 100 degrees Celsius. Now you might say, how is that possible? We're putting heat from the bottom. Aren't we heating up the gas? Well, we have to have idealized systems for these engines. Okay, in reality, it might increase temperature just a little bit, and the shape of the diagram will look a little different. When you study thermodynamics for real, you get into all these realities. But what we're saying here is this is what we call an isothermal process. What this means is that when we're on this curve, we start in this state with the piston down like this at a very low volume and a high pressure. We increase the temperature there, and the temperature is going to want to put energy in. That's what this means. We're putting energy into the gas, and so the gas does work on the piston, and so the piston goes up. Where does the energy come from to raise the piston up? It comes from the hot source down here, agitating the air molecules inside and pushing the thing up like this, right? And during this process, because we're raising the piston level, we're saying the temperature of the gas stays at 100 degrees Celsius. You might say, well, how so? Shouldn't it increase the temperature? Well, if you continually increase the volume, then the energy that you put into the gas, it just goes, instead of going into temperature, it goes into raising the level of the piston. I'll say that again. Instead of the energy from heat going into increasing the temperature, like if everything were fixed, since you're allowing the piston to move, that energy instead just goes into raising the piston. So it's conservation of energy. The energy you put in is essentially going into work done on the piston. So that's so important that I'm going to write down, I think, right over here. I'm going to put a little arrow right here, and I'm going to say gas does work on piston. Now, in real life, we want to build engines that do work, right? We care about work for us. So positive work is what we consider when the gas does work. The gas is the working fluid in this case. The real engines can work on any kind of fluid, lots of situations. But in this case, the gas is the working material. What we want is we want the gas to do work on the piston, which is the environment, or going into the environment. We want this thing to spin. And the gas, when the gas is increasing its volume, the gas is pushing up and it's doing work on these crankshafts here, and it's turning this this cog thing here, and so it's basically doing work by changing it into rotational motion. So the gas is doing work on the environment being the crankshafts and the whole thing turning like this. The gas is doing work on the environment. Okay, so what happens when it gets to the very top like here? If we were to stop, and if this were not a cycle, and we just stopped right here, how much work did the gas do on the piston or on into the environment? How much did it do? Well, you might remember, I'm going to come back to this diagram in a second. You might remember from basic physics or from basic calculus if you take either of those things. And if you haven't taken it, it's okay. I'll explain it to you. If you have distance and force, like if you just push a box across a room, like here's a box, and here you have some force on the box, and then later the box moves here, you're still pushing on it, and the box moves some distance d, right? So what you basically figure out is that you start at a position of 0 and the box moves to a final position right here of like, I don't know, 5 meters away, and the force is constant the whole time. Because it's force times distance, it's the number force times the number of units of distance, in that case 5 meters. So when we say work is equal to force times distance, we say that's the work done on the box, right? And we learn in calculus that that's the same thing as the area under this curve, right? Because it's a rectangle, right? So you have force and then you have the number of distance units. And so it's the area under the curve, under the force distance curve, that tells me how much work was done in this case. What if I have a more complicated situation? Like if I have a more complicated situation like this, like there's some distance there, or some position, I guess I should say, and then force right here. Let's say that it still goes from 0 and it still ends, the box ends in 5 meters, but the entire time I'm pushing on it, I'm not pushing with a constant force. Let's say I start out at at some force, 10 newtons, let's say, but then immediately I get very tired, and then I end up pushing the rest of the way at like 5 newtons of force. And then I get really tired and I just gradually peter off like this. What's happening here is I'm still pushing in the same direction. I'm pushing really hard, and then I'm pushing less hard, but I'm still moving the box down the way. And then I get really tired and I just gradually stop pushing, and then I end up in the same location. So you can't just take force times distance, because the force is not constant. So when you get into calculus, you learn that what we really want to do, since it's the area under this rectangular situation that gave us the work, in calculus we learn how to find the area under these super complicated looking shapes, and the area of this thing is the work done. Like work done on the box. It's always the area under the curve when you're plotting the pushing force done in newtons and the distance a box moves. But we just said, just a minute ago, that pushing a box with some number of newtons times some number of meters gives you joules, but pushing a piston with a pressure and a change in volume also gives you joules. So can you see where I'm going with this? If we want to figure out what the work done by the gas doing it on the piston, as the piston gets bigger and bigger and higher, the gas is pushing up on that piston, how much work is done? Well, what we would do, I don't want to mess my diagram up, I would draw some dotted lines down here, some dotted lines down here. The pressure is like the force acting, the volume is like the distance sort of moved, and the area under this curve, I would calculate it using calculus, but it would literally be the area under this curve, which would be the gas, the work done by the gas on the piston or the outside environment, and we would call it positive work. Because I'm a human, I want this thing to do something for me, so when the gas does work on the piston and it starts it to move, when the gas does the working, then we call it positive work. Hold that in the back of your mind. The area under this curve, the whole curve all the way down here, would give me the work done by the gas on the piston. Now, here's where I need you to use your imagination a little bit, because this is not idealized. Now the piston is at the highest possible position, highest volume that it has. That's why it gets to here. And whenever it gets down to this point, what we do is we instantaneously drop the pressure of the gas. Now nothing in real life can happen instantaneously. Everything takes time in reality. But in an idealized engine, we say once the piston gets to the top, which means that this piston is now in contact with the cold reservoir. Then the cold reservoir is immediately in contact with the gas and immediately lowers the temperature of the gas immediately, like in a nanosecond or something. So what that does is that tends to lower the pressure of the gas immediately. Now the volume is going to stay the same, but what would happen is the pressure would drop. Notice the pressure was right here, but now the pressure drops to a lower value, and it happens at a constant volume. We call this point C right here. All right, and so what we're basically saying is that once the piston gets all the way to the top like this, immediately the temperature, not the temperature, the temperature of the gas immediately drops. What is the temperature of that cold reservoir? Let's just say it's 0 Celsius. We did use liquid nitrogen and stuff, but let's just say it's 0 Celsius for now. And once it gets cold, what's going to happen? That gas immediately, it's a constant volume, it drops pressure. And when you have dropping pressure or lower pressure, you have less force being pushing up on that piston, essentially. Now, this piston has inertia. You can even see it when I turn it. It has inertia. It wants to keep going. Now, eventually, it's going to slow down. Once it reaches the top and it kind of bends over like this, it's going to start compressing the gas again. But the gas is now at a lower pressure. We're at this point. So it tends to compress the gas. That means it lowers the volume of the gas. So when we're at this point right here, it tends to lower the volume of the gas and in the same breath increase the pressure. Because when you squeeze gases, generally the pressure tends to increase again. So we get to this point, we immediately lower the pressure of the gas, and because we've lowered the temperature of the gas, we're at the cold plate location, and we immediately start compressing the gas again. Now, I want to put here that this is the place when this thing is in contact with the cold reservoir, which we're saying is ice cubes, let's say 0 degrees Celsius. So this would be the case when we were running it on boiling water and on ice cubes on the top. Right? So we immediately cool off the gas, immediately. The pressure is immediately lowered, and the inertia coming from the energy of the previous cycle starts compressing the gas again. That means the volume goes down and the pressure goes back up when you compress it. So here I need to draw some arrows just to make it 100%, I think, clear. Here we're going this direction, like this. Then we're going this direction, like this. Then we're going here, up here. I can even put another little arrow right here if you want, like here if you want. So we're going to be going and tracing a cycle out right here, right? And this process is happening with the gas being at a constant temperature of 0 Celsius, all right? Now, when we're doing this part of the cycle, what is happening? See, over here, we were putting heat into the gas, and the energy coming in was really what was pushing the piston up. But whenever we're going the other direction, what is happening during this? Are we putting energy into the gas? Are we putting heat into the gas? No, we are now touching the cold reservoir. So what we're doing is we're taking heat out of the gas. We put all the heat in. That is what made it rise up. And then when it touches the cold reservoir, we start taking heat out of the gas. We cool off the gas, right? And so what we're doing in this phase is during this part of the cycle, we are taking heat out of the gas at the cold reservoir. Because it's touching that plate, heat is going out. So here we have putting heat into the gas. That's making the volume get bigger. Here, heat is coming out of the gas, and that is making the volume go smaller along this path. All right? Now what's going to happen when we get to this point? Here we have reached almost basically one full cycle. Just to start over, we start here, we get to this point, right? Then at this point, we immediately cool off the gas, and now we're compressing the gas again. During this part right here, the gas is, let me go up here, the gas is being compressed like this, and the volume is going down and the pressure is going up. Now we're essentially back where we start, but we're in contact with the hot plate again. And that means, since we're at this point, we're in contact with the hot plate, this is point D, and then right here we reconnect, and we basically immediately raise the temperature back to 100 degrees Celsius again, because we have now closed the cycle, and we have raise the temperature of the gas instantaneously again. So I'll put another arrow right here. All right, so we said that only on this leg going down that the gas was doing work on the piston. We were putting energy in, the piston was raising. I'll do it again. Piston was raising up, we're doing work on the piston. But then when we start going down, the gas is no longer doing work on the piston, because the gas, even though the pressure is lower, the gas is still trying to push the piston up, but the piston's overcoming it and squishing it and going down. When something is pushing and its volume or distance is going counter to that, then we no longer say the gas is doing work on the piston. We say the piston is then doing work on the gas. When you're compressing that gas, you're doing work on the gas. Now we bookkeep that as negative work. Positive work is when the gas does work on the environment, but negative work is when the environment does work on the gas. Now, different books and classes, you could use the exact opposite sign convention, but this is the one I'm using for this explanation here. All right, it'll work out either way, but I just wanted to point out, some people use different convention. So during this part of the cycle, the piston does work on the gas. So what we do is we bookkeep this as positive work that the gas does on the piston, and we bookkeep this as negative work, which is work done on the gas. In other words, the gas is still trying to push, right? But the piston is squishing it down because it's taking energy from the previous cycle and it's squishing it down. So we call that negative work. How would we find out how much negative work is done on this part of the path when it's compressing things? Well, we would find the area under this curve. We'd drop it down, we would find the area just like before, but we would bookkeep it as a negative area, right? A negative work. So during this part of the process, we would call it a positive work, which would be the area of this curve all the way down to the axis here. During this part of the cycle, we would find the area all the way to the axis, we would call it negative work, and we would take the positive work minus the negative work, and what we would say is that the work that lies between what we call the area in this PV diagram, this is the work done by engine. The net work done, right? Because in this cycle, the gas is doing some work, but on this cycle, there's some work being done to recompress the gas, so that's negative. That's not active work done on the environment. We subtract the two, and the bigger this area is in the center, the more work is done. And now you can see that the temperature here and here yield the boundaries of the PV diagram, and so to get more work out of the engine, you want the biggest area you can get inside the PV diagram. That will mean your engine is doing more work. How can we get more work done? Well, if we have a wider envelope between the hot and the cold reservoirs, then we'll basically have these curves farther apart and we'll have more work done. And that's why we saw up to a limit of freezing our engine that when we put wider and wider temperature gradients, it seemed to run faster, right? And that is essentially the point of thermodynamics. That's essentially the point of this whole lesson. I wanted to start off with how this little thing was designed to run. It was designed to run on a cup of coffee, just like a warm liquid, and it just kind of like cruises along a little bit. But then we went and we added boiling water, and we saw that it moved faster. Boiling water would basically be moving the hot reservoir up here, giving us more work coming out, right? Then we said, well, we'll just go ahead and put ice cubes on the top, and then dry ice, and then liquid nitrogen to cool the top faster and faster, or I guess more and more, to be able to shock the gas and cool it down faster when the piston gets up there. And that would be like lowering this. So lowering this is putting ice on the top, raising this is like putting hot water on the bottom, and then the combination of the two gives us more area in our PV diagram, gives us more work done by this engine. There is a lot more I could say about this. You could have a whole career studying engines. I mean, people do that. This is just one type of engine. There's many types of engines, but thermodynamically speaking, whether it's a car engine or a jet engine or whatever, they essentially run on a gradient of temperature. If you have this engine running where the temperature up here and the temperature down here are the same, which is like it is now in my hand, what's going to happen? Well, it'll sit there and spin due to inertia because I put energy in with my hand, but it's going to stop because there is no gradient to drive any movement anymore. You have to have something hot and something cold to put energy in to cause it to go up, and then something on cold to take energy out, and the difference between the energy in and the energy out is essentially going to be some fraction of it converted to work, as we saw with the efficiency there. All right, remember, this is an idealized discussion. Real PV diagrams do not look like this. This is idealized. This is not a Carnot engine. It's not the maximum efficiency possible, but I think it gets the point across. I hope you've enjoyed it. Drop me a line, let me know what you think, and follow me on to the next one.
Learn anything at mathandscience.com.